Hi everyone. We're just going to go over the workshop problems. This is from workshop 6, workshop number 6. So all right, so number 1, this is problem number 1. These questions are pretty straightforward. We're just calculating improper integrals. How to do that? The way to do this, of course, is that integral from 14 x over x ln x cubed is equal to the limit as b approaches infinity of integral from 14 to b of dx over x ln x cubed. We now have a problem that's fairly easy to solve by u substitution. Because of course, as I said, if it were a definite integral, but what we've done, of course, is convert this into a limit of definite integrals. So let's let u equal ln x, du is equal to dx over x. So what we can now see is that this is going to equal the integral of u over u cubed. Now, I have to put in the limits of integration. We can see is that if u equals ln x, the bottom limit of integration should be ln 14, and the top limit of integration should be ln of b. So this now becomes, this is going to be negative u to the negative 2 over negative 2. I'm just doing that a little bit in line, but we know that 1 over u cubed is equal to u to the negative 3. So you simply proceed from there to find the antiderivative in the normal way. So that's going to be from ln 14 to ln b. Oops. One other thing that I want to do here, I don't want to forget about this. I'm going to put in limit as b approaches infinity. Let's move this over to the right. This is also the limit as b approaches infinity of that. People often ask me this, and this is a Calc 1 kind of question. People say, do I really have to write the limit every time? So even though I didn't do it, answer is yes, you do. There's a very specific time that the limit comes out, which is when you evaluate the limit. So until then, yes, you actually do need it in there. So this is going to be the limit as b approaches infinity. So on b of, I'm going to substitute now. This is going to be negative negative 2 over negative, why did I put that extra negative sign in? It's not a negative, that's going to be negative 2. And then minus we have ln 14 to the negative 2 over negative 2. So that equals limit as b approaches infinity of, you can see here is this first term is going to be written as negative 1 over 2 ln v squared. And then I'm subtracting a negative, so let's just make that positive. And this is going to be 1 over 2 ln 14 squared. What we can see here is that this term actually is going to approach, 0 because natural log function grows to infinity as b approaches infinity. So we have negative 1 over something that's becoming infinite. So the entire fraction there becomes 0, and we are left with simply 1 over 2 ln 14 squared. And there we go. So that's the answer to part A. Now part B. The integral from 1 to infinity of dx over 1 plus x squared arctan x. The thing to recognize here is this is also a really nice u substitution problem. First, let's set up the limit. This is limit as b approaches infinity of, limit as b approaches infinity of the integral from 1 to b dx over 1 plus x squared arctan x. And let's let u equal arctan x and du equal dx over 1 plus x squared, since that's the derivative of arctan x. And what we can see now is that we have limit as b approaches infinity of integral from 1 to b of, this is just du over u. So that equals the limit as b approaches, forgot to change the limits in integration. Mistakes that I tell you guys you're never allowed to make. So the arctan of 1 is pi over 4. That's the angle whose tangent is pi. The angle whose tangent is 1 is pi over 4. And here we're just going to have arctan of b is yet, but we'll see how to deal with that in a minute. So this is going to be integral is limit as b approaches infinity of ln. So this is going to be ln view going from pi over 4 to arctan of b. That's going to be the limit as b approaches infinity of, this is going to be ln of arctan b minus ln of pi over 4. So the thing that you have to recognize here is, first of all, this is just a constant, so that's just going to be ln of pi over 4. This, as b approaches infinity, arctan is going to approach pi over 2. You can kind of see, not leave myself enough room there, just a second. You can kind of see why that is, because if I graph the arctan function, it looks like this. Pi over 2, negative pi over 2. It has two asymptotes, but what you can clearly see is that as x is approaching infinity, the arctan function just gets closer and closer to pi over 2. So this is going to equal ln of pi over 2 minus ln of pi over 4. Using some log rules, that gives us pi over 2 over pi over 4 like that, and pi over 2 divided by pi over 4 is just 2, so the answer is ln 2. Okay. Next problem asks us to write several inequalities that can be used with the direct comparison test. What we're trying to do is, let's be clear on what these inequalities have to look like. For the comparison test to work, we have to be able to write something like 0 is less than f of x is less than g of x, like that. So we have to be able to show that both of these are positive, which is not going to be an issue in any of these cases, really. So the 0 part, I want you to state it, but it's not necessary to actually show it, other than just to pay attention to the fact that it's there. The issue is that one of these is going to have to be a p integral, or rather the integrand for a p integral. I'll explain in a minute what the difference is there, just to make sure that everyone's on the same page. The idea is that if I'm trying to show that g diverges, then I want to show that it's greater than a known p integral that also diverges. If I'm trying to show that f converges, then I want to show that it's less than a p integral that converges. So let's do the first one of these. Let's do a, which is integral from 1 to infinity of x squared over x squared over square root of x to the 7th plus 5. I want to show that that converges. So first thing to do is try to get an intuition of what the p integral is going to look like. The answer is that we want to focus on this part, the highest powers in the denominator, taking into account all roots. So it's certainly the case that this expression here that I've written, which is the integrand, it's not the integral, it's the integrand, and it is approximately equal to x squared over the square root of x to the 7th, which equals x squared over x to the 7 halves, which equals 1 over x to the 3 halves. So what I'm trying to say here is that when we let x greater than infinity, that plus 5 is not really going to matter very much. So we're going to be able to more or less disregard it. We're not going to be able to disregard the powers of x. We're not going to be able to disregard the fact that we're taking the square root, but we are going to be able to disregard this constant that's going to just amount to almost nothing next to numbers that are getting close to infinity. So this is not an answer, what I've written. What I've written is not an answer. Don't give this as the answer. The point is, this is the intuition as to why this is going to be the correct p integral to compare with. I now have to actually show that the integrand is less than this p integral, which, by the way, we can see that this is a convergent p integral because p is equal to 3 halves, which is less than 1, less than or equal to 1. Or sorry, less than 1. Less than 1 is the criteria for convergence. So what we can do now is, let's actually show how to generate the correct inequality. So first of all, let's observe that as x is going to infinity, x squared is positive, and the square root of anything is always positive. So I can certainly write that 0 is less than x squared over the square root of x to the 7th plus 5. Now, what I want to observe is that if I'm making the denominator bigger, then that means that I'm making the fraction smaller. So this plus 5 is making this fraction smaller than the fraction square root of x squared over square root of x to the 7th. Now note that this is not the same stuff that you see directly above it. And above, what I'm doing is I'm just focusing on the higher powers and saying that that's probably what the integral that I want. That's probably what the integrand that I want to compare this integrand width is going to look like. On the bottom, on this line, what I'm doing is I'm actually making an algebraic argument that this has to be less than this. Let's keep going. We can simplify now and say that x squared over x to the 7th is equal to x squared over square root of x to the 7th is equal to x squared over x to the 7 halves, because I'm just translating that root in power. And now I'm just going to apply the law of exponents. Since 2 is like 4 halves, if I take x to the 4 halves over x to the 7 halves, I get 1 over x to the 3 halves. So what I have here is all the elements of the inequality that I need. I have 0, less than, the integral is less than, and then a whole chain of things that leads to that. So I can finally state the answer, which is 0 is less than or equal to x squared over x to the 7th plus 5, which is less than or equal to 1 over x to the 3 halves. Why is it less than or equal to 1 over 3 halves? Because it's less than or equal to something that we later show is equal to 1 over x to the 3 halves. So this is the inequality. All right, let's do B. So this is the integral from 2 to the x to the 5th plus 1 dx over the cube root of x to the 18 minus x. Okay, so here what I want to do is I want to show that this diverges, which means that I'm going to need to show that this integral, this integrand is greater than a known convergent integral. So I can do this actually without intuition, because I'm just going to be able to use this sort of process to construct the right inequality. So let's do this. Let's observe that x to the 5th plus 1 over the cube root of x to the 18th minus x is greater than or equal to. I mean, the theorem allows for greater than or equal to, even though really it's greater than. It's greater than or equal to x to the 5th over the cube root of x to the 18th minus x. Now, how do I know that? Well, because the only thing that changed was this. In other words, it certainly makes sense that if I add 1 to the numerator in some fraction, it's going to be greater than the same fraction without 1 being added to the numerator, because that can only make it bigger. So it's certainly the case that this is greater than this. Now let's keep going. Notice how this subtracting x is just making the denominator smaller than it would have been. So by making the denominator smaller, I'm making the overall fraction bigger. So if instead I decide not to subtract x from this under the cube root sign in the denominator, I'm going to get a bigger fraction. So I can say that that's greater than the cube root of x to the 18th. Now I have an expression I should be able to simplify. This is going to be x to the 5th over cube root of x to the 18th is x to the 6th. And by division, this is just 1 over x. And we, of course, know that for x going from 2 to infinity, which is the interval of integration here, that's certainly going to be greater than or equal to 0. So we now have, if I flip it around, which I'm going to do, I'm going to focus on this, this, and then there's, then this. Because what I've demonstrated now is that 0 is less than 1 over x is less than the original integral. 0 less than or equal to 1 over x less than or equal to x to the 5th plus 1 over cube root of x to the 18th minus x. And of course, this is a p integral if p is equal to 1, which we know diverges because 1 is less than or equal to 1. So what I've shown is that the given integrand is greater than or equal to, but really greater than the integrand of a known divergent p integral. So this is the correct inequality that we were looking for. So we have this problem, which is to prove that x over 2x cubed minus x converges. I'm just going to write this up here because I want to emphasize something. A lot of you are going to look at this and go like, oh, this is easy. Just write x over 2x cubed minus x plus or equal to x over 2x cubed, which equals 1 over 2 x squared, which is just 1/2 times 1 over x squared. And I know that if I integrate 1 over x squared, I get a finite number. So certainly 1/2 times that finite number is still a finite number. And you'd say, I'm done. What's the problem here? The problem has to do with the word wrong, which is that this inequality is wrong. This is not a correct inequality, and you can't form a correct proof with an inequality. It's not true. Because here what I'm doing is I'm making the denominator smaller by subtracting x, which means I'm making the fraction bigger. So it's certainly not going to be the case that the fraction on the left is less than or equal to the fraction on the right. So that's not the correct way to do it. This is the correct way to do this. What you want to do is start by reasoning for an interval for x greater than or equal to 1, which is the interval we care about because that's the interval of integration. So that interval is certainly the case that x is less than or equal to x cubed. Everyone agree with that? So if that's the case, then it's also got to be the case that negative x is greater than or equal to negative x cubed. And if I add 2x cubed to both sides, I get 2x cubed minus x is still greater than or equal to 2x cubed minus x cubed, which by the way is equal to regular x cubed. So if that's true, then focusing on this and this, we can certainly write that 1 over 2x cubed minus x, when you take the reciprocal, you're going to flip the equality so it becomes less than or equal to 1 over x cubed. And you can certainly write then that if I multiply both sides of this inequality by x, since x is still a positive number in the interval 1 to infinity, I get x over 2x cubed minus x is less than or equal to x over x cubed, which equals 1 over x squared. So what we now have is looking at this expression, we can see that for the number 1, we have 1 over 2 minus 1, which is 1. So that's certainly greater than 0. If I let x get very large, I'm still going to have a positive number on this side because we know that x cubed is greater than x, and therefore 2x cubed must be greater than x, so the denominator is never going to become negative. So this is going to be 0 is less than or equal to x over 2x cubed minus x, which is less than or equal to 1 over x squared. We have here a p integral with p equals 2, which is greater than or equal to 1. So there we go. That's this is the inequality that you're looking for. It's like that, and that's how you form it. All right. Number D. This is a fairly important problem. It's come up in a lot of contexts, especially in chapter 10. Over. Now, the reason I put this in here is that I have to get you out of the idea that the way to solve any problem is to calculate a value. We cannot calculate this. I do not know how to calculate this integral. So what you need to recognize is that sine of anything is always between -1 and 1. So as I think I mentioned in the video, last year you learned the squeeze theorem, and you learned that this was a fairly important principle because sometimes we want to evaluate a limit by squeezing it between two other limits that we know. I don't want you to think that therefore what I'm asking you to do is evaluate a limit. I'm not. This is just another principle where we can use an inequality to evaluate, where we can use an inequality to prove a statement. So here, the thing to recognize is that sine to the fourth, which is an even power of sine, is always going to be between 0 and 1. So what I can say is that, let's write out the inequality this way. So first of all, let's observe that 0 is less than or equal to sine to the fourth x over x squared plus 1. Why? The denominator certainly has to be positive because x squared plus 1 is always going to be at least 1. And on the top, we know that sine to the fourth of anything is never going to be negative because any real number that I raise to the fourth power is going to be either 0 or positive. This e to the x in here is kind of a red herring because it doesn't matter. We certainly don't know really much about what the graph of sine to the fourth e to the x looks like, other than the fact that it's bounded between 0 and 1. I'm sure that the actual pattern of oscillating back and forth looks like a real mess, but it doesn't matter. The point is that I know that sine to the fourth e to the x is going to be between 0 and 1. So therefore I know that sine to the fourth e to dx over x squared plus 1 is going to be between 0 and 1 over x squared plus 1. It has to be less than or equal to that because sine to the fourth e to the x can't be any greater than 1. So we now have this, and now I can simply observe that 1 over x squared plus 1 is less than or equal to 1 over x squared, and I now have my inequality. 0 is less than or equal to the given integrand, which is less than or equal to 1 over x squared. The lesson here is you have to get out of the habit of thinking that the best way to solve a math problem is to evaluate a number. That's going to stop being true right now. And until the very end of the course, when we get to polar and parametric forms, there's almost no question that we're going to ask that involves actually calculating a value, except in situations where it's particularly interesting, and I'll show you those. But very much of what we're going to be doing is going to be about proving things about values that we cannot calculate. This is one of those. Okay, go to number 3. We're finally there. So does the integral from 0 to 1 of 1 over x to the 1/2 plus x squared converge or diverge? So recall that this is in fact an improper integral because its integrand is unbounded on the interval of integration. What this function looks like, if you were to graph it, is sort of like this. So we do in fact have an unbounded integrand, even though the interval of integration is not. So the thing to recognize here is a couple of things. First of all, recall that the p integral rule is different for the interval 0 to 1 than it is for the interval 1 to infinity. It's actually backwards. We'd say that for the interval 0, 1, or more generally 0 to the a, p integral converges for a p that's between 0 and 1, and it diverges for p greater than or equal to 1. It still diverges in both cases for p equals 1. But the point is that what we can say is that the integral of 0 to 1 of 1 over x to the 1/2 converges, and the integral from 0 to 1 of x over x squared diverges. So what I'm challenging you to do is ask which one of these is going to be more important. It turns out that thinking about more important is actually not the right paradigm. The important thing to understand is that if I write that this purple integral, let's say that this is y equals 1 over x to the 1/2. If that's the case, then if I add something to the denominator like x squared, what I'm doing really is just I'm making the function smaller. So I'm making the curve lower than the purple curve. So that means that this is y equals 1 over x to the 1/2 plus x squared. And what we know is that if the integral of the purple curve converges, then anything that's less than that but still positive is also going to have to converge. That just makes sense that if everything under the purple curve adds up to a finite number, then certainly everything under the blue curve also has to add up to a finite number. So the correct argument goes like this. What we're going to say is that 0 is less than or equal to 1 over x to the 1/2 plus x squared, which is less than or equal to 1 over x to the 1/2. We can now say that integral from 0 to 1 of dx over x to the 1/2 converges because it's a p integral on 0 to 1 with p equal to 1/2, which is less than 1. And therefore, something that's less than that, but still greater than 0, is certainly going to converge. So therefore, we say integral from 0 to 1 dx over x to the 1/2 plus x squared converges. Okay. Now let's go to number 4. This is one of the more interesting problems. I like this one. So let's consider the curve y equals 1 over x to the 3/4. This is another one of these curves that has this kind of shape. It's just it's the integrand of a p integral. So let's find the area under the curve on the intervals 1 to infinity. So there's 1 to infinity like that. What we want to do is find this area and find this area, and we're going to state that it's infinite. So let's evaluate that. Say the integral from 1 to infinity of dx over x to the 3/4. Now I don't even have to evaluate the integral P integral of P. This is P integral of P is equal to 3/4, which is less than or equal to 1. So this diverges. And we can see that the area is infinite. Okay, B. The question is now, suppose that I take the volume of revolution formed by taking this curve and wrapping it around the x-axis. The shape you get here is kind of like this. It's like sort of like an infinitely long trumpet, kind of. I don't know if I'm drawing this in a way that's meaningful, but you could think of the wide end as like the bell of a trumpet. And the question is the volume of that infinite trumpet, is it infinite or is it finite? Now, I know that I've given this actually as a test question and also as a quiz question. And I get answers like, well, we already saw the area is infinite, so certainly the volume can't be infinite because volume is bigger than area. This is where, I mean, intuition is a great thing, except when it's wrong. So the only way to do this really is to set this up as volume integral. So volume is going to equal pi times the integral from 1 to infinity of 1 over x to the 3/4 squared dx. That's just volume by the decimal. That's going to equal pi times the integral from 1 to infinity of dx over x to the double 3/4. So it's starting to look like that integral is actually going to be finite because we have the integral with 1. For the value of the p integral on the integral 1 to infinity, and the formula is just 1 over p minus 1. So this is just going to be pi, so I have a pi outside there. This is going to be 1 over minus 1, which is pi times 1 over 1/2. That's going to be 2 pi. So you actually get a finite amount of volume. It's kind of interesting because if you imagine that I've taken my infinite trumpet and I have a picture on my wall of the infinite trumpet, the area of that picture is infinite, but the object that's being depicted holds a finite amount of water. How can that possibly be? Think of it this way. If I had painted a picture of my infinite trumpet, I'm going to have, this slashed area here is going to have to be painted with paint, and that paint is going to have a thickness of, let's say, 1 millimeter. No matter how far I go to the right, it's going to have very short height of paint, but coming out of the page, there's still going to be, let's say, a millimeter thickness of paint. On the other hand, when I form the infinite trumpet, the trumpet actually gets skinny in both directions. In other words, if you think about the cross section of the trumpet, it's going to be circles that keep getting smaller and smaller and smaller and smaller and smaller and smaller like that. Whereas the slices of paint like this, they keep getting shorter like that, but they're still the same. They still have the same 1 millimeter thickness coming out of the page. I'm getting this very small like that. But if you imagine that, this is a piece of paper and that's out of the page, what you can see is that, actually that's not really a very good way of drawing it. Yeah, there's no good way to draw that. The point is that if little slices of paint, they're all the same thickness, even though their heights get to be different. Like that. And I want to be clear, this is not the thickness dx in either case. This is just the thickness of the paint. This is the thickness of the paint coming out of the page is the same. So I don't know if that makes the explanation any better. There's a name for this phenomenon. It's called the paradox of Gabriel's horn. I guess this infinite trumpet is Gabriel's horn. We usually do this in imagining the surface area of the trumpet. It turns out the surface area of the trumpet is infinite. The volume is finite. Here, because we haven't got done the formula for surface area yet, I did it just in terms of area looking at a picture of the trumpet. But it's the same point, is that it's the same point that the trumpet has an infinite area and a finite volume.